Hi guys, Tim's back again. Nice to see you. This is for my AS students, right? AS students, I've already done this video before, but it wouldn't flaming upload. I did it in the lab, so I'm having to do it again. If you're going to look at haloalkanes, not if, when you look at haloalkanes, right? You will, this is the video to start with. This is the very first video in the sequence. This is the last topic really, guys, that you do at AS on haloalkanes, and it sort of merges into the organic chemistry side of things. So start with this video on haloalkanes as an introduction, then move on to that stuff about the atmosphere and the ozone layer, and then look at that laboratory sort of experiment that I showed you with separation techniques using a separating funnel, and by all means look at other things because that sort of thing does come up. About how you separate different mixtures and that type of thing, so look at that. But haloalkanes, vital, very important. Let's just quickly sort out what you need to know. Okay, I can put my pen there. Right, so haloalkanes. Start with this video. Okay, right, what are they? Right, C, X. X can be generally not fluorine, because the carbon-fluorine bond is very strong. They're quite unreactive. That's why they're used as chlorofluorocarbons. CF bond doesn't do a lot of chemistry, really strong. So X is probably Cl, Br, or I. And that creates a polarity in the bond because these are quite electronegative. So you're going to get a delta plus, delta minus. Whenever you get that type of charge variation, where it's even if it's a double bond, that type of thing, that's where the action occurs. So electron rich areas such as a carbon-carbon double bond, they'll undergo electrophilic addition. If you remember, they're attractive to electrophiles because they've got areas of negative electron density, negative charge. This has got an area of delta positive charge, and it's going to be attractive to something called, which we haven't looked at really, nucleophiles. Okay, nucleophiles are attracted to carbon delta pluses. Okay, so right, let's have a quick look then at this nucleophilic idea. Interestingly, primary, secondary and tertiary still can apply to haloalkanes. So primary haloalkane might be something like this, I don't know, CH3, CH2X, the thing being that the carbon, that's a primary one. Okay, two hydrogens on it and a lump of, well, a methyl group on there. Secondary, something like this, X, which we don't really need to bother, but they do exist, so it's worthwhile knowing them and visualising them and seeing them. There's your secondary right there. Translate it. I'll go this way because I think it's easier to see in the sun. Anyway, there, R dash, X, secondary. Tertiary, same idea, coming down here. Hopefully you can see that. Methyl, if you will, whatever. Another methyl. Tertiary. Okay, so now we don't really need to bother too much about these, but they have implications. I believe that the tertiary one is the fastest because the intermediate, if you will, is more stable. Tertiary tends to be more stable. That's why they're resistant. Tertiary alcohols are resistant to oxidation, that type of thing, and that's why tertiary carbocation is favoured with Markovnikov's rule. Tertiary is going via a tertiary intermediate is more beneficial. That's not the right word, but better. It's the best intermediate to go by, and you meet it across the range of organic compounds. Okay, so you can get primary, secondary, tertiary, but I wouldn't worry too much about that. Right, let's get rid. I know you can just see me back, so it's a bit awkward, but job done, job done, job done, job done. There it is. Okay. Right. Straight in. Right. Different. So, what do? Right. They do this. Nucleophilic. This nucleophilic is a big deal. Nucleophilic substitution. It's your last mechanism. Okay, nucleophilic substitution. So what's a nucleophile? Right, nucleophile is an electron pair donor. Right, and there's lots of different nucleophiles, so they've got to have an electron pair to donate. Sometimes they're charged, sometimes they're not. I'll go over here a bit, out of the way. Sometimes they're charged, sometimes they're not. But so let's see. Nucleophiles could be, probably the classic is the hydroxide nucleophile. That's a biggie, right? But you can have nucleophilic attack using maybe chloride or bromide or iodide. They can all work as nucleophiles. They've got a lone pair. They can act as nucleophiles. Those are the two main ones. You could argue that ammonia, which is certainly a nucleophile, is AS, but it tends to come up. There's no charge on ammonia, but it acts as a nucleophile. It tends to come up at A2, and you get good at these, and you'll be able to just use whatever. So those tend to be ASs. A2 nucleophiles. Cyanide nucleophile, extending the carbon chain, don't worry about it, AS. Hydride nucleophile, able to reduce carbonyl compounds to primary, secondary, nucleophilic addition, don't worry about that, AS. And is there another one? Probably. I need to extend this argument, so probably ASA2, don't worry about those. These don't even worry about that at the moment. We're talking about perhaps these two. Nucleophilic attack, that's the name of the game with haloalkanes. Okay, so what do? It's very quick, but actually appears a lot. The mechanism is this. Any old haloalkane. Let's do a bromo one. Okay, put on it what you like, right? H, doesn't matter. Methyl, don't make no odds. Because what matters is this, delta plus, delta minus. Now, what you do is you take a nucleophile, hydroxide. So I'll show you the mechanism, I'll show you the overall equation. So basically you need to react it with sodium hydroxide to give your hydroxide nucleophile. In it comes, look, and straight away, and remember, these arrows are a movement of a pair of electrons, they're not a movement of anything else. A pair of electrons there, bang, attack. Those pair of bonding electrons, lone pairs attack, bonding pairs do that. Result of that movement, it's a one-step mechanism, so it's a lot easier than the alkenes mechanism, certainly a lot easier than that homolytic free radical stuff. Right? You end up with your product. That's it. OH, there. Br minus, there. You've gone from a haloalkane to an alcohol. Every time you've got like a halogen joined to a carbon, you can effectively swap it, substitute it for an alcohol group. Okay, and that's something. When I'll do an overview to see how all this fits into everything else. Okay, but that's very common reaction that happens very quickly. So you could do an overall equation for this. So we will. Now, sodium hydroxide, warm it, reflux it, not too bothered. That will give you a nucleophile, but this isn't the mechanism, it's the overall equation. You will form an alcohol, so you're moving to different functional groups, whatever. It doesn't matter, as I keep saying, you're swapping your halide, if you will, for an alcohol group, hydroxyl group, if you will. Plus, and of course, it's very nice, NABR. So Br minus picked up, NABR, it could be KBr, whatever. So that's overall equation for nucleophilic substitution. Okay, now, okay, right, that brings me on to an experiment, really. How do you compare how fast these things go? Okay, right, well, I'll get rid of this. Where's me board rubber? I've lost it. God, it's annoying. How can I work in these conditions? Hey? How can I work in these conditions? Right. You'll see this in the book, you'll see this on thing, comparing rates of hydrolysis. Comparing rates of hydrolysis of haloalkanes. Right, this comes up, you'll see this in the pack. You're going to get a pack sent, which I want you to do. Okay, so make sure you keep all this stuff that you're doing so that we can assess and see how you've got on later, whether you've managed to do them, because at some point I want to see these packs, guys, done and completed. So this will come through via the email. All right, so what we're going to do, right, you compare 3 haloalkanes. Okay, we tend to compare chlorobutane. I'll try and do it in one hit, which is, okay, C4H9Cl. We're going to, number 1, we're going to compare it with, sorry, I'm not concentrating, bromobutane. Number 3, Haolo butane. So, fair test. Now that reaction I showed you, that mechanism, we're going to do the same. So we're going to take these and we're going to sort of warm them if you want. Now this is called hydrolysis because we're actually using an alkali, acid hydrolysis, alkaline hydrolysis. Okay, but they're always sort of boosted by, like I say, an acid added or an alkali added to get that hydrolysis going. So though it's called hydrolysis, splitting up by water, it's actually really, to me, it's the hydroxide that's doing the splitting up, the hydrolysis. So what you do is add sodium hydroxide to them, or potassium hydroxide. I can't remember the experimental details, it doesn't matter. I think you can warm it with the sodium hydroxide and you will get nucleophilic substitution, okay, using the hydroxide nucleophile. You'll form this. You'll form this. You'll form this. And you'll see nothing. Because the chloride, the bromide, and the iodide are substituted, kicked out. There. You need, if you're going to compare rates of hydrolysis, you need that this experiment will definitely be on YouTube. You need something visual if you're to see how fast a reaction goes. You need to be able to observe something, evolution of a gas, colour change, mass loss. Measuring the rate of something needs a visual observational parameter that you can keep your eye on. So where's the visual thing here? Answer. You put a bit of silver nitrate in. Now you know this because this fits onto what we've already done. And what will happen is the chloride, when it is released, the rate of it released, it'll immediately latch on to the silver ions that you've put in solution, and you will see a precipitate of silver chloride being made. You will white precipitate. You will see a precipitate of silver bromide being produced. You will see a precipitate yellow of silver iodide being produced. In other words, the solution will go cloudy as the reaction proceeds. You won't see much difference in these colours because it's not an identification of them. We know what they are. It's an idea of a rate. So you do that, and what will happen? No problem at all. Let's put some numbers on. So you've got 3 test tubes, each with these in. You add some sodium hydroxide in, put some silver nitrate in, sit them in a water bath, and watch the precipitate, watch the cloudiness develop within the solution. Okay, it's all good stuff. There. So you will see them going white and cloudy. What goes first, right? So answer. Let's put some numbers in. These numbers are made up. Fastest, iodo haloalkanes. followed by, say, 60 seconds later, so it'll go cloudier first, second cloudy, bromobutane, third cloudy, slowest of all, 90 seconds, say, chlorobutane. So in other words, that leads us to this, effectively, this conclusion, which is whatever it's attached to, CI, whatever, okay, will react faster than CBr, which will react faster than CCl. Fastest, middle, slowest. Okay, that is the rate of hydrolysis. You need to write that down. That the rate is iodo fastest, bromo second fastest, chloro slowest. The fluoro bond, CF bond, I don't think it ever gets to precipitate because the CF bond is so strong it doesn't actually break the bond. It doesn't actually, the reaction doesn't occur. So we're only comparing these three. So fastest, slowest. I'll write that on. Okay, now, so you need to know that. Look on YouTube, look on experiments. They'll show you the actual experiment. I can't do an experiment, I can't do a video experiment because I can't get in my lab. So we've had that. So that's gone. Leading us to, let me just check that my video is still going because I'll be fed up if it isn't. Oh no, still going, happy days. Right. What factors affect rate of hydrolysis? Why? In other words, why CI is faster breaking, to put the OH on, than CBr, which is faster than CCl. Why? Okay, well, it's very simple. Bond enthalpies. CF bond enthalpy, delta H BE bond enthalpy data, kilojoules per mole. CF, CL, CBr, CI, sorted. Bond enthalpy, massively strong, 430, don't break, needs a lot of encouragement. Weaker but still strong, I think you know where I'm going on this. Weaker still, weakest of all. Okay, bond enthalpy is the dominant factor. So in other words, A-level question would be this, right? Explain why iodo haloalkanes react faster than bromo haloalkanes, which react faster than chloro haloalkanes. Answer: because you've got to use this terminology, the bond enthalpy of iodoalkanes is much lower than bromo or chloroalkanes, therefore less energy is required to break the bond, not weaker, lower bond enthalpy. Less energy is required to break the bond, therefore the reaction will be faster. Okay, the weaker the bond enthalpy, the faster the reaction, and that gets asked. So I want you to have a look at that, guys, and sort that out. Okay. I think that'll do on that. I got cut off a little bit when I was doing the ozone stuff, and I wanted to finish that off. Well, I have sort of finished it, so I've done a lot of the haloalkane stuff. There will be packs sent to you. Have a go at doing them. We'll leave it at that for now, I think. Okay, cheers, guys. See you later. Happy days, all right?